Okay, hold on. Okay. Okay, so there's a feature on the lives that if you start, I have to pause that because I can hear myself. If you start in portrait mode, then it's got to stay in portrait mode. So hopefully, let me just double check this on the other cam and then we can get started. Okay, so we're just going to have to be in portrait today because once we've started, there's no way to fix it. People on TikTok, you're in portrait anyway, so you get the normal stream. Okay. Hopefully that's okay. We're just going to be in portrait. You get to see more of my awesome ESA hoodie. So this is my Zombie Crew hoodie that I'm wearing because yesterday was Dark Matter Day. I don't actually need to be wearing these anymore, actually. Yesterday was Dark Matter Day. I was supposed to do a stream, but then my flight got cancelled, so I did not get back in time in order to do the stream, so it got moved to today. So thank you so much for joining. And the theme today is dark matter, but we can answer questions and talk about anything to do with physics, particle physics, that you want to ask. I think we've got Bob again in the live stream who's going to be handling the questions. So he's from Fundamentally Explained. So thank you so much for joining again and helping sort out the questions and also moderate the chat. Yay, hi Bob. So let me give a quick introduction about what's been going on. So on Monday, the Large Hadron Collider beams dumped for the last time in 2023. So this is regular planning. So we always close down over the winter in order to do maintenance and repairs of the LHC and of the experiments and of the accelerator complex. And also so that we don't use so much energy over the winter when people need to heat their homes when it's getting colder here in Europe. So that happened on Monday. There is going to be a live stream by CERN, I think tomorrow, about the heavy ion run. So they're going to be live in all 4 of the different control rooms and talking about the heavy ion run and also the end of data taking for this year. So you should absolutely go and check that out. We'll make sure that there's a link in the chat and also in the post live chat that you can go and take a look at so that you can go and watch that stream. There's also going to be a live by CERN about dark matter, and I'm going to talk about dark matter in a moment. I didn't manage to grab the link to that. If I remember rightly, it's going to be over on Twitter, but the best thing to do is to make sure that you're following CERN, and they will announce this live as well. So that's going to be a chance to learn more about dark matter from them and some other of my colleagues working at CERN talking about dark matter. So that will be really exciting. Also, I'm going to be talking, when I talk about dark matter, about Euclid, the Euclid mission. So this launched on the 1st of July this year. I was very lucky to go along to the launch event with ESA and see the excitement of the people who were working on the Euclid mission. And so it's arrived at its destination at L2, which is the Lagrange point 2. And it's been calibrating and getting ready to take its data. It's going to be a 6-year-long mission. And the team with the Euclid mission are going to release their first color photos next week. I think that's on the 7th of November. So that's also going to be really exciting because this mission is going to help us to understand dark matter better and also dark energy, because it's also looking at how the expansion of the universe is happening over time, which is linked to dark energy. So yep, that's the news that I wanted to share today. There's obviously loads more going on as well. So if you have questions about anything to do with particle physics or about CERN, please do let me know. I'm going to get rid of this video here so I don't have to watch myself because I already have 2 screens of myself in front of me. I don't need a third on the left as well. So I will launch into the questions in a minute. What I wanted to do first is to give a bit of an overview about dark matter. So if you're just finding the stream and you don't know so much about dark matter, you don't know where to start with your questions, that's absolutely fine. That's what I'm here for. And so I wanted to talk about what dark matter is, a little bit about the evidence that we have for it, because we do have evidence for dark matter. We just don't know what it's made of. So let's get started with some of that. I took notes to make sure I didn't forget anything. So if you see me looking down, that's because I want to make sure that I give you all of the information that I want to share. Good, I thought my notes app was going to shut down then. And yeah, while we're doing that, if you ask questions in the chat, and then we're going to be collecting those so that we can answer some of those later. So dark matter is an invisible matter in our universe, and we've known about it for the last, since sort of the 70s. So there, I didn't write dates in my notes. So when they were measuring the rotation of galaxies out in space, what you expect is when you're measuring something rotating, you expect it to travel slower as it moves further out from the center of the rotation. So they were looking at the rotation of galaxies and plotting the speeds of the things in the galaxies as you went from the center of the galaxies further out. And what they expected to see was sort of a rising peak, and then for it to go and sort of drift off. It would be the other way around for you, I think. And what they actually saw was that it was a rising peak, and then it kind of went flat. So the rotation, the speed of objects as you got further out of these rotating galaxies was the same. It wasn't decreasing like it was expecting. And that gave the hints that there was dark matter or some invisible matter that we weren't measuring with our telescopes in these galaxies, causing that speed to be different. And one of the scientists who did a lot of these measurements and really, showed the scientific community that this is what they were measuring was Vera Rubin, who was really instrumental in these measurements, especially of the galactic rotation curves. We also have other evidence showing that there is some invisible matter in our universe. And that is that when we look again out in space, so we do measurements out in space, so there's an effect called gravitational lensing. And what this is if, for example, I point my telescope out towards something very, very far away, and there is a galaxy in between the thing I want to measure and my telescope. So it's in the middle, right? And the effect of that large amount of gravity from that massive object means that light is bent on its path towards us. You get like a gravitational well, and the light's path is bent on its way towards us. And so we get this really interesting lensing effect of the light. And so if you have a galaxy right behind this one, so you've got two galaxies, one here and one further away, don't know if you can see all my hands. The further away galaxy, its light gets sort of ringed around the one that's in between us. So you get these really interesting lensing effects that are because of the mass that's in the way. And what they found was this lensing effect was greater than the amount of matter that we expected there to be in the way. So again, there's more matter that we're not measuring with our telescopes, but that we are seeing the effect of due to the way that the light is bent when it comes towards us. There's other evidence as well for dark matter. So we can look at the very, very early universe. This is called the cosmic microwave background, and it was accidentally discovered, which is one of my favorite experiments. I remember hearing about it when I was an undergraduate. The cosmic microwave background was accidentally discovered when they were trying to do some measurements, and they kept getting noises in the equipment. And hold on one second, because I want to tell you the correct names of the scientists, because their names have escaped me right now. Yeah, so it was Penzias and Wilson. were doing this measurement, and they had their equipment and it was very, very noisy. It was noisier than they were expecting to be, and they thought there was pigeon poop in their detector. And they actually went inside and their telescope and cleaned this pigeon poop out because they thought that's what was causing the noise in their measurements. And it turned out actually it was from this ripple, this echo of the very early universe that they were able to measure, called the cosmic microwave background. And now that we can measure this, there have been a number of different satellites that have gone outside of the Earth's atmosphere to measure this background, this microwave background. And the later the satellites are, the more precisely we can measure it. And we get this beautiful picture of the very, very early universe. And we can model, we can simulate how the distribution of this microwave background should look, and fit it to the data that we actually observe. And the simulations include a certain amount of dark matter in them. That's how they're doing these predictions. And the simulations fit the predictions fit the data very, very precisely with a certain amount of invisible extra mass in our universe. And also there's another set of evidence, which is the sort of cosmic web, since it's one day after Halloween, this cosmic web that's throughout our universe of dark matter, and how the structures of the galaxies, how where they're located in our universe, where they're placed. And we can also simulate this, and the simulations show that we must have this invisible matter in our universe. And there's about 5 times more dark matter in our universe than there is regular matter. So there's a whole bunch of scientific evidence that there is something in our universe. We have measured it, we've measured its effects, but we don't know what it is. And so this is one of the greatest mysteries in physics right now, and it's really fueling a lot of experiments and a lot of scientists to try and understand what this dark matter is. There are different ways that we can look for dark matter. So we can look for, in my research, in the Large Hadron Collider experiments, we are colliding the matter, regular matter particles, we call them standard model particles, and we could collide them together and predict that if in the early universe dark matter was created from the everything colliding with each other in the early universe, then maybe we could create it in our experiments with the Large Hadron Collider. And just to say that if we could create it in our experiments, it's already being created in collisions of high energy particles from cosmic rays coming and colliding with our atmosphere. And so it's natural, it's all around us. If there's dark matter in our galaxy, which we believe there is, then we are swimming through it right now. And so creating it in our experiments would just be a tiniest drop in the ocean compared to all of the dark matter that's out there. But if we could create it in these very controlled conditions, then we might be able to get a better understanding of what it is. So in the Large Hadron Collider, we would collide protons in this case, coming in at very close to the speed of light. Oh, I see one quick question here that says, why isn't it called unknown matter? I don't know who got to name this thing, but they called it dark matter because they didn't know what it is. It's mysterious. But invisible matter is a much better name for it, or unknown matter. So yeah, we have these protons that come in, they're traveling at almost the speed of light, and they collide together in the center of our detectors. And then with this energy, we can create new particles, or potentially new dark matter particles. And when I say we can create, we don't really get to control what happens. That's all quantum mechanics. We're just creating the conditions, and then quantum mechanics decides what's going to come out of those collisions. And one of the key features of dark matter is that it doesn't interact with normal matter. It doesn't, otherwise we would have seen it with our telescopes through its other forms of interaction. So far, we only know about it due to its gravitational effects. So if it's formed in our detectors, we're not going to measure it in our detectors as dark matter. What we're going to find is that there is something missing that we expect to be there and then we don't see. So we have to look for conditions where we can say that there was a collision that happened, but that stuff was missing from our detector. One of the ways that we can do this is, for example, if some dark matter is made, but also some standard model particles come out of that. We've set up our experiment. So that the momentum is zero in one of the planes of the detector. And this means that then if when we're measuring all the stuff that comes from the collisions, if a lot of it is coming out in one direction and there's nothing or very little coming in a different direction, that tells us that something escaped the detector that we weren't able to measure. And this could be dark matter. But there are other particles in the standard model that could also leave our detector without being measured, and that's neutrinos. So we know that we create neutrinos in our detector, but we can't measure them because they very, very rarely interact with anything. So this is what we call background in our measurements, and we have to account for all of the different regular matter ways that this could show up to be able to look for dark matter and say that actually dark matter was found in our detectors. There are other ways that you can look for dark matter. So you could also have dark matter particles coming in and interacting with each other and creating standard model particles. This is one of the ways that, for example, the AMS, the Alpha Magnetic Spectrometer on the International Space Station out in space, is looking for hints of dark matter. It's looking for additional standard model particles that are more than that we predict with just the standard model events, and that this could then come from dark matter. So that's another experiment that's looking for dark matter. And then there's also direct detection, where you have a standard model and dark matter particle interacting with each other, and then they then have another standard model particle coming off from that, maybe more dark matter, and then you could look at this sort of deflection of the standard model particle in your detector. So there are many different ways that we are looking for dark matter, and really it's because it's this big mystery in science, we need to approach it from all different angles in order to be able to find it. It's a truly global effort to be able to understand what this dark matter is. There's also the Higgs boson that we discovered with the ATLAS and CMS experiments in 2012. And I already said that dark matter interacts gravitationally, that it has mass. And because the Higgs boson is the mechanism that gives mass to standard model particles, perhaps it's also the mechanism that dark matter gets its mass. We don't know for sure, but it's another route that we can look for dark matter, is by looking at the different ways that the Higgs boson is produced and interacts with other particles, and looking for either, again, something missing, so fewer Higgs boson events, or some other difference from our prediction of standard model only events. So the Higgs boson could be a link, a way to study dark matter and potentially understand it better. And all of this that I've been saying assumes that dark matter is a particle. And as a particle physicist, that's the way I'm going to treat it, because that's how I can look for it. But there are other hypotheses of dark matter, which include things like modified gravity, and also that it could be very tiny primordial black holes. And so we really need the whole community to be understanding what dark matter is, to be looking for it in all of the different ways that it could be created. So that is a whirlwind explanation of what dark matter is. Hopefully that gives you a little bit more information. Maybe it was too much information in one go, that's fine. So I'm going to have a look at some of the questions that have come in and start answering that. So please, if you have questions about dark matter or about anything to do with CERN or physics, just drop it in and we can chat about it. So let me bring that up, and I'm going to drink my tea in the process, and I have a very bad habit of always making my tea too large, too close to the rim. So I'm going to try very hard not to spill it on myself. I just saw a really nice comment on TikTok about a young woman who's aspiring to be a scientist. So thank you very much for your kind comments, and I can't wait to see what you achieve in science. Right, so there's so many questions. Thanks, Bob. So let's get launched in. So I kind of answered the first one that we've got here from YouTube, which said, do you think that dark matter is a modification of gravity or a weakly interacting massive particle? So as I said, I am a particle physicist. So ask a particle physicist what they think it is, and they're going to say particle physics, because that's how we think about the world. So, I mean, yeah, to me it makes sense that it's a type of particle. But one thing I didn't say is that it doesn't have to be one type of particle. It's not like it's just going to be a one dark matter particle. There could be a whole dark sector of matter that are lots of different, if it's a particle, lots of different types of particles that make up the collection that is dark matter. So once we start to unravel and be able to find some dark matter particles, if it is a particle, then hopefully that would lead to even more understanding. So the next question I see is not about dark matter, but the question is, if the collider is shut down, does that mean you get a really long vacation? So no, sadly not. It doesn't mean that we go on a 4-month vacation or 3-month vacation, depending on when the restart happens. Mini restart. It's not like a big restart, but it's the year start. What happens is that the people that work on the accelerator and on the detectors then perform maintenance and operation checks, calibrations, that kind of thing. So they're going to be busy doing that. And the Large Hadron Collider has shut down, but the actual accelerator complex is still running. Parts of it are still running for another couple of weeks. So yeah, the Large Hadron Collider has now been switched off for 2023, but for example, the Antimatter decelerator that we have, ELENA, is still going to be running because we're still performing measurements in the Antimatter factory, which is a real thing that we have at CERN. And there are also, other measurements still going. So we have Isolde, which is a nuclear facility producing nuclear isotopes to study at CERN. That's also going to be running for a bit longer too. So it's not completely shut down yet, and we also don't go on vacation because we have a significant amount of data that we've been collecting, not just this year, but throughout run 3 and also in run 2 and run 1 of the Large Hadron Collider. And it takes us a very long time to process this data because it's not only a huge amount of data that has to be processed and understood and calibrated, but some of the processes that we're looking at are incredibly precise, and the systematics, which is understanding the machine and how the particles are measured in our detectors and the different ways that they can show up, that's also a really incredibly complicated procedure that we have to do very carefully in order to not trick ourselves into thinking that we found a new particle when we haven't. So we're very meticulous when we do our analysis, and it can take years to perform these analyses. So we don't take a very long vacation, and we're analyzing the data, discussing what we found and how we can publish the results from our research. And everything that we do at CERN is published online for free and in open access. So I understand that's not fully accessible to people who haven't been working on this kind of data for a long time, but it is published online, completely open access. And then we also are happy to explain it if anybody has any questions about the research. So because we're very all of our results belong to everybody. So there's another question here from YouTube, and then I'll jump to some from TikTok as well. So is dark matter any relation to Hawking radiation? So Hawking radiation is the radiation that comes from the outside of a black hole. And no, this isn't any relation because that is something that is in the visible light spectrum. I'm not an expert on black holes. If you want to ask somebody about black holes, you should go and check out Dr. Becky. Her channel is absolutely fantastic, and she is an expert on black holes and can tell you all about Hawking radiation. But it's not the same as dark matter. So there's a question on TikTok. Please tell me your computer is RGB lit. So I do have a desktop computer, but it's at CERN or in Geneva. So unfortunately, I don't have it with me. Otherwise, I would show you it because it is RGB and it's very cool and it makes me very happy to look at. My computer is very, very shiny. So there's a great question here. Do particles in the LHC, when they approach the speed of light, gain relativistic mass? This is a question where you have to be careful, even as a physicist, how you describe this, because people are very particular how you phrase it. So I would say no, they don't gain relativistic mass. What they do gain is energy. So as the particles get more and more accelerated close to the speed of light, their mass stays the same, but the energy of that particle increases. And then that's how we can perform the collisions at the high energies that we need to in order to be able to do our studies. So there's another great question. Can you overview why we have both dark matter and dark energy? So the short answer is we just like calling things dark when we don't understand them. I say we, I was not involved in the naming of these things. Again, as I said, dark matter would be better named invisible matter. It's a much more accurate way to describe it. We have them both because these are two huge questions in physics. In fact, the dark matter and dark energy combined make up 95% of the matter energy density in the universe. So the standard model, the regular matter stuff that we do understand, is only 5% in our universe. It's such a tiny amount that we actually truly understand. So there's loads more still to explore in our universe. And dark energy is what we call the effect of the expansion, the accelerated expansion of the universe. And we don't really understand that either. We understand that even less than we do dark matter. But it's something that as a scientific community, we are working on understanding better. And dark energy is much more related to cosmology. But that's another great time to mention. So my mug is actually the Euclid telescope. That was launched, as I said, on the 1st of July. So this is something that Euclid is going to be trying to understand, not only dark matter, but also dark energy. So it's going to be measuring the redshift of galaxies and looking back really much further. It's going to be looking a lot further back into the universe, the lifetime of the universe, but also across a large spread of the sky. So if I remember correctly, it's a third of the sky that it's going to be imaging. And this is going to allow us to understand how the universe has been evolving over its lifetime in even more detail. And it's also going to be looking for the distribution of galaxies and understanding how galaxies are distributed over time in our universe to understand dark matter as well. So Euclid will soon be launching its full color images, and it's going to spend 6 years surveying the sky and hopefully give us more, it will give us more information about dark matter, that then as a particle physicist we can incorporate that into our models, our predictions, to be able to see if we can understand dark matter at a collider level as well. So we're really approaching the same, I didn't even get to drink my tea, hold on. So we're approaching the same problem but from different angles to try and understand what dark matter is. So there's a good question here that says, we look back to see the start of the universe. Why do we not look back, not look forward to what is happening at the edge of the expanded universe? So the thing is that because there is a finite speed limit of the speed of light in a vacuum, everything we see, absolutely everything you see, is in the past. So the fact that I hold my mug up in front of me, what I am seeing is this mug as it was fractions of a second in the past, not as it is now, because it takes a finite amount of time for light to travel. So we're always looking back into the past. So we cannot look out towards the edge of the universe or the edge of the visible universe, because as we look further and further out into the universe, we're looking further and further into the past. So this is why we talk about being able to look into the past of the universe, because of this finite speed limit of the speed of light in a vacuum. We are just looking further and further out and looking further and further back in time. So it's not possible to look into the future. So I'm just reading because this question is a little bit longer. So this one is, so I'm going to come back to this one because I think this requires a longer answer. So I'm going to think about it and then come back to it. So I'm going to go back to another dark matter question, which is, do you think dark matter interacts with other dark matter through an as yet undiscovered force? I mean, I don't want to speculate because I'm an experimental physicist, so I like to have data. So what we do know is that dark matter interacts gravitationally because it has a mass and it has an effect on the light that's traveling towards us. It's possible it could be interacting with itself in other ways. If we were able to find that there was another force in our universe, so for example, there's the G-2 experiment in the US, which is looking at the wobble of muons. So there's an accelerator and there are muons in the accelerator, and it's looking at how they wobble in the accelerator. And this wobble is affected by the vacuum of space and the other particles that exist in our universe sort of popping in and out of existence as they do all the time around these muons and affecting the way that it wobbles. And we can very, very precisely predict this wobble, and the measurement that came from the experiment is ever so slightly different. And it could, if we continue to get data that makes the precision on these two, on the measurement and then also on the theoretical prediction, as that gets improved, if they continue to be different, then that could hint that there's another force or another type of particle in our universe. So it's still early days. The experiment is incredibly interesting, but we do need more data on this to be able to say what's going on in the situation. But there could be other ways to find out if there are other forces or particles in our universe, and then that could then potentially, again, it's very much speculation, be something to do with dark matter. So we have to perform these experiments, and what I think is really nice about the G-2 experiment is that it shows that there are different ways to search for new physics, we call it, in our universe. We can look like we did with the Higgs boson for a bump in our data, this new particle at a certain mass that we discover that wasn't there before because we couldn't create it. We didn't have the energy to create it. I mean, it was there before in our universe, but not in our data. Or we can do very, very, very precise measurements of things that we already well understand and look for the tiniest deviations between the predictions and the measurements. And this is something we're also doing at CERN, looking for dark matter by looking, for example, at how the top quark and the Higgs boson interact with each other. So these precision measurements help us to understand our universe very, very precisely. I'm just going to drop in and say, by the way, that if you are enjoying this stream, if you're watching it live or if you're watching it later, if you're enjoying it and could give me a thumbs up, that would be really helpful, because that means then more people get shown this video and get to learn about physics. So that would be really amazing. Thank you very much. And if you're not subscribed already, I mean, on YouTube, you have to be for the chat, just so that we can keep things nice and fun. But if you're not subscribed already because you're watching this later, please do go ahead and subscribe, and then you get more physics videos in your feed whenever I post a new video, and that really helps out the channel as well. So there's the plug. So there's a really nice comment here from YouTube from someone who is hoping to go and study physics at uni, and they want to specialize in particle physics, and her dream is to work at CERN, and the question is, how did I end up in particle physics? Wow, and her teacher helped build the accelerator for Atlas, which piqued the original interest. So it's really exciting that you are interested in particle physics. I think that's fantastic. I can very quickly say a little bit about my journey into particle physics. So I did a physics undergraduate degree at the University of Manchester in the UK. And while I was there, I was still trying to decide where I'm going to go, as in what direction I'm going to take my physics career. I thought maybe I would go into astrophysics and into space, because I absolutely love it. But when I was at Manchester, I did my master's project in the D0 experiment, which is, it's on the Tevatron in Fermilab in the US. So it was the predecessor to the Large Hadron Collider, which was based in the US. And I was measuring the top quark for my master's, and I just absolutely loved the research. I loved the international environment, getting to work with people from all over the world. And I was just, so excited about the research that I then wanted to stay and keep doing it. And so I did my PhD at Manchester and moved to the Atlas experiment. And then since then, I've worked in a number of different countries on various postdocs. So, and now I'm in the Netherlands at NICEF and the University of Amsterdam, and hopefully based there for a very long time. So I'm also teaching at the university, so that's really fun too. So if you want to work at CERN, the best thing you can do if you want to be a particle physicist, because there's lots of other ways that you can work at CERN too, but if you want to be a particle physicist, then going and getting first an undergraduate degree in physics, and while you're there, take advantage of every single opportunity to apply for the CERN summer student program, to apply to try and visit CERN as part of your studies. If you can do your master's project on one of the experiments at CERN, that will really set you up well as well. But also don't be afraid to try some other things at the same time. So the thing about the summer student program is it's amazing, but it also depends where you're from, because we don't have, I mean, the summer student program prioritizes member states of CERN. So otherwise it's even harder to get in. But I don't want that to put you off. You should absolutely 100% apply, always apply every single opportunity you get, but also apply to a bunch of other stuff too, because just getting international research experience, working with different scientists is incredible experience, and will really set you up for the next steps as well. So just, my advice is to apply for everything, have a great time, do lots of research, and learn from as many people as possible. So I also see, so there's a question here. Thanks, Bob, for putting the summer student program in the chat, and it's currently open for applications. So if you're watching this and you are an undergraduate in physics, go and check out the link that Bob put in the chat, because you should 100% apply for this. I did not apply to be a summer student at CERN because I worked in my summers. So I worked minimum wage jobs to make money for the rest of the year. And people told me that it's competitive, and it is. But you have a chance to get in, and you deserve to give yourself that chance to get into the program. And so, yeah, I didn't apply because I didn't think I'd get in. And now I'm working at CERN, and I would have had a good shot of getting in. And so I should have applied, and I didn't. So I think you should apply and give yourself that chance, because it's a great experience. It's super fun from everyone I've heard that went to the summer student program. And they pay you to go on this program. So it's funded to go, and you get to spend a summer in Switzerland working with a whole bunch of scientists, learning from lots of international people, and hanging out by the lake in Geneva. So it's a lot of fun. And then I should really mention as well, and I didn't give Bob this link, but I'll put it in the chat later. There is also, so I never ask for any donations during my lives, because I also believe with the CERN ethos that what we do is open, and so I don't hide anything behind subscriptions or paywalls or anything. But we do have the CERN and Society Foundation. So if you did want to support anything that we're doing at CERN, and you do have a bit of spare cash to give, then that's the place to send it, because they also have a program that is supporting non-member state summer students to go to CERN. And I think that's really important, to be able to make sure that science is accessible to everyone, from no matter where they come from. And so that's a really great program. And if you have a bit of spare cash, you can send it towards them and support a student from a non-member state going to CERN. And they have a whole bunch of other great programs happening as well with the CERN and Society Foundation. So yeah, if you want to support anything that's happening at CERN, then that's the place to send it. All right, I'm sure I'm missing a whole bunch of questions. I'm trying my best to do as many as I can within the hour. So there's a question here. So I'm going to go for some more dark matter ones first. So is dark matter a form of exotic matter? So yeah, I mean, we don't know what it is. We only know that it interacts gravitationally, so we can give it any name that we want, and exotic matter is a way that you could describe it. But until we're able to sort of find hints of what it's made of, then yeah, we don't know what it is, and we can keep naming it, but we need to find out more information about it. So also, welcome if you're just joining. If you haven't seen any of my videos before, I didn't start this, I just launched right in. I was so excited to talk about dark matter today. My name is Clara, and I'm a particle physicist working at CERN, and I love to talk about physics and particle physics. So thanks so much for joining the chat and joining the live today. And yeah, I'm going to take a look at some more questions. So yeah, there's a great question here. Do we know how dark matter is distributed? Is there more of it in the middle of galaxies or around it? This is a really good question, and I don't 100% know the answer. I know that it is clumped around galaxies. It sort of forms a halo around the galaxies, but I don't know, for example, if there's more in the middle or on the outside. Because when I'm searching for dark matter, I'm thinking about it as being potential particles in our collisions. So I would have to look up exactly the distribution in space. But it is also not uniformly spread throughout the universe. It does clump together because it has gravitational mass. So it does gravitationally attract each other and form clumps as well. And this is how we see the structure of the galaxies throughout the universe. And then there's another question: can dark matter and dark energy be a property of a specific region of space? I mean, I think I don't know for sure. The short answer is we would need to know more about it to be able to say. I think it's not. We could talk about local and universal. We'd have to learn more about it to know what its properties are. It's a good question, but I don't know. Oh, there's a great. Okay, there's two great questions I saw from TikTok. I mean, they're all good questions, but there's two that caught my eye. So, what are the real-world applications of the Large Hadron Collider? One of them, okay, not the Large Hadron Collider, that's of CERN. One of them I was going to say that we're using right now. So, the World Wide Web was developed at CERN, but that was way before the Large Hadron Collider was built. Some of the real-world applications to hadron colliders, not at the scale that we do for the Large Hadron Collider. The LHC is 27 kilometers long as you go around, which is about 16 miles, but a bit over 16 miles. But if you shrink down and have a small hadron collider, or a small hadron accelerator, then you can use that for medical applications, and specifically you can use it for hadron therapy. And hadron therapy is a form of cancer therapy where instead of, when you have radiation treatment, you want to destroy, for example, the tumor, cancer tumor, and because of the way that cancer works, because it replicates so often, when you irradiate it, it gets damaged more than healthy tissue does. But if, for example, you're irradiating it with X-rays, then you're still going to the healthy tissue doesn't want to be irradiated by X-rays. But if you can use a hadron accelerator, and hadrons are like protons inside of atoms, or other types of heavier hadrons, then when you deposit the energy of the hadrons, it's, rather than it being sort of a uniform distribution, it's a peak. So you have a peak of where the energy is deposited. And so what you want to do is send all of that energy into the tumor and try to not have, or have as very little as possible into the healthy tissue. And then the ideal situation is if you then either rotate the patient or you rotate the accelerator around, and then you really focus the energy on the cancer tumor and not on the healthy tissue. And that's really, I mean, it's great anyway, but for example, if you have a tumor in your eye and you really 100% don't want to irradiate the brain, because that's pretty important, then things like hadron therapy can be a much more precise way of irradiating tumors in the head, for example. So that's just one way that accelerators can be used. Particle accelerators can be used for medical applications. You can also use the detectors that we develop for our experiments for medical detection. So PET scanners, positron emission tomography scanners, which are using antimatter to look inside the human body, use detector technology that was developed at CERN. So that's some of the technology that we're developing. We don't patent anything. We tell everybody about everything that we develop, and then that can later be used for medical applications, for example. Okay, and then there's a question, how do bananas make antimatter? So this is another one from TikTok. So bananas have potassium in them, and potassium can decay and change into another type of particle and give off a positron. And so this is then antimatter that is coming from bananas, because they're heavy in potassium, and also avocados. And so if you eat a banana, then you have antimatter inside you, or can be generating antimatter inside you. Okay, so there's another, I'm going to jump back to a dark matter question from YouTube. So there's one saying, can you talk about the hypothesis that the standard model Higgs is a portal to the dark sector? Is the search still going on with Atlas and CMS? And I'm going to be very clear here that when we say the word portal, especially in this case, it does not mean like a Stargate. That would be super exciting, and if we had one, I would totally show you. I'd be going on so many adventures. But when we talk about it, we mean like a link or a bridge, in terms of a way to use the standard model Higgs boson to understand dark matter. And so I'm not sure quite when the question came in, but this is what I was talking about earlier, about how because the main thing that we know about dark matter is that it interacts gravitationally, and therefore it is massive, and that we know that the Higgs boson, the standard model Higgs boson, gives is the process by which standard model particles get mass. Perhaps it's also the same for dark matter, or maybe there are other types of Higgs bosons. There could be more of them. There are theories in particle physics that predict this, and perhaps then dark matter interact with those as well. So that's why also, I mean, we want to understand the Higgs boson as much as possible, because it's still a new particle, even though we've had it for a decade. There's still loads that we want to understand about it, how it interacts with different generations of particles that we have in the standard model. But it could also help us understand dark matter too. So there's a question here that so someone said that they saw a PhD position under my supervision at NICF. Are there more upcoming positions? So I hope that, I mean, part of the process of being an academic is that I have to apply for funding in order to be able to hire more people to work with me. And I hope that that is successful over the next couple of years. But I have to wait to see if I have more positions opening. But there are lots of positions opening at NICF in general, and my colleagues are fantastic. So if you ever see any positions for NICF and you're interested in particle physics, I 100% recommend applying for those too. And in general, if you're interested in particle physics and, for example, the experiments on the Large Hadron Collider, then there are lots of really great positions that open up. And then if you end up at CERN, then we'll be colleagues and we'll maybe bump into each other in the restaurant. Oh, there's a question here as well. What is the lingua franca at CERN? Mainly German or English or another? So the main language at CERN, there's actually two official languages at CERN. One is English and one is French, because CERN is based in France/Switzerland, and it's the French-speaking part of Switzerland. So one of the official languages of CERN is French. The other official language is English, and depending on which department you're in, is which language, that then depends which language you're gonna hear more of. So a lot of the science is done in English in terms of the particle physics research, for example, because there's not only the people based at CERN, but there are people all over the world doing this research. It's a truly international endeavor. And so most of the science, the particle physics, is done in English, but what you will find is that people based at their local institutes will speak whatever language of the country they're in. So for example, my Dutch still needs some improvement, but Dutch is spoken a lot at NICF and at the University of Amsterdam. When I was in Germany, there was, a lot of meetings that were in German, and in France, there were meetings in French. So people speak to each other in whichever language they're most comfortable in. But then when we have group meetings in Atlas, like collaboration meetings, all of those are held in English. But if you go over to the engineering side of CERN, a lot of that is done in French. So if you're thinking of working at CERN and you're not necessarily just looking at the particle physics, improving French is also a really great piece of advice, I would say, to help give you an extra opportunities of working at CERN. So there's a question also, can data scientists apply for an internship? So yes, when I talk about the summer student program, it's not just for particle physics. It's also for data science, engineering, and a bunch of other of the programs that we have at CERN too. So Bob put that link in the chat, and you should go and check it out and go and see all of the different departments that the summer student program is for. And we also have the technical student program, which is then being based at CERN for a full year or up to a full year. And that I also know that you can be a data scientist for that as well. So I definitely recommend going checking those out. So there's another good question about dark matter. Is the dark matter distributed more than would be suggested just from a bunch of black holes? I'm not 100% up to speed with all of the dark matter, the black hole side of the dark matter research, but as I understand, it cannot account for all of the distribution of dark matter. But I'm not 100% sure, so I don't want to upset any colleagues who might be watching. So let's have... Yeah, so there's a question here, because I was talking earlier about being a member state of CERN. So there are certain countries that contribute more to the budget of CERN, and so then there's some priority for certain positions because of where the funding comes from. How could you get into a program? So if you're not from a member nation or associated to CERN, how could you get into a program from CERN? So I have so many colleagues who are not from, their nationality is not one of the member states at CERN. And I mean, one of the best ways to be able to work at CERN is you can work for a university who then sends you to CERN. And that's what happens. That's how I'm working at CERN. So I'm employed by the University of Amsterdam, and they send me as a member of the Atlas collaboration to work at CERN. This is the most common way that people are working on the experiments on the Large Hadron Collider. So then it doesn't matter what your nationality is. If you go and work at the university, you can work at CERN. So I would recommend checking out different departments in different universities that have research that you're interested in, and depending on your career stage, applying to work with them. And then this would be how you can then go and work at CERN. That's the most common route to be able to work at CERN. So there's also a question from TikTok saying that they worked for a particle physicist as an undergrad, and can I walk them through what I do every day? So I would say that for everybody's day is very different. I go to a lot of meetings. We have a lot of discussions in particle physics, and this is just one of the features of being an international collaboration with over 5,000 people. We spend a lot of our time discussing the research that we're doing, discussing the calibration methods, the data processing, and people presenting results. So somebody will work on something for a couple of weeks, and then they will present as a virtual presentation mostly now. But also, I mean, they still happen in person, but again, everybody's all around the world and travel. We don't want to be traveling all the time. So people present the research that they do, and then we discuss it and talk about the different ways that it could potentially be improved. And then also, when I was a PhD student and first postdoc, I was doing a lot of work on the detector, on the Atlas detector directly. And so I spent most of my day then in a clean room, and I was testing new components for the upgrade of the Atlas experiment. So then I would be wearing a white coat and often a hairnet, and be very carefully calibrating these detectors, and then I would send them off to be irradiated and test them again. I do a lot of coding day to day, so I'm coding my analysis. So with the large amounts of data that I have, then I want to be able to select the data that I'm interested in. So for example, if I'm looking at top quarks, then I want to be able to look for the different decay products of the top quark, the way that it changes into other particles, to be able to isolate the signal I'm interested in, and that requires programming of the data. I think that's a lot of the day-to-day. Meetings, data processing, being in the lab, lots of coffees, to talk with people in person as well. So it really depends what kind of, if you're interested in going into particle physics, it also depends how much you want to be doing programming, computer programming, and how much you want to be in a lab working on the hardware directly. Okay, let's have a look at what other questions there are. So there's a question here. Are there more engineers or physicists in CERN? I don't actually know the number. That's a good question. I think probably employed by CERN, it's gonna be maybe even numbers, but overall I would say there's more physicists, because there's over 5,000 people in my collaboration, most of whom are physicists. So yeah, I would say probably mostly physicists at CERN. So there's a question, what do I think about using Twitch as a live Q&A? I mean, I already am on 2 platforms at once right now. So I don't want to build another platform for doing lives. I try to answer as many questions as I can. I mean, we're almost at the hour already, so I will have to wrap up soon-ish, not right away, but soon. I do think there are better ways that I could be collecting questions, and I am planning to look at ways that we could maybe have people like questions as they come in, so that the ones that more people are interested in can float to the top. I mean, Bob's doing an excellent job at pulling out questions from the chat, and I know it's really difficult to catch everything. But if you feel like I missed your question, please put it in not in this live chat that you see, but please put it in the actual video chat afterwards, and I try and go back and answer as many of those as possible, or drop it in one of my other videos, and I will try and answer as many as possible there too. So I'm sorry if I miss the questions. It's just we have a limited amount of time. Yeah, and also I watch streams on Twitch, but I haven't yet decided to stream there myself. Oh, so there's a question here. How do you isolate specific particles to collide? So we don't select which of the particles are colliding. For example, with the proton runs that we do, so we just finished the heavy ion run, but for the proton runs, we have a gas of hydrogen, and we eventually strip the electrons away. There's a process where we add extra electrons and then we strip them away, and we're left with just the protons from the hydrogen. And then we process this throughout the accelerator complex, and we get bunches of protons in the Large Hadron Collider where there are 100 billion protons in each bunch. And then we have lots and lots of bunches in each beam of the LHC, and there are two beams going in opposite directions. And when they are brought to collide in the center of the detector, we don't pick which protons get to collide. It's like, imagine two swarms of bees flying towards each other. Some of them are going to hit each other, and we can decide generally how many of them are going to collide each time they cross by squeezing the beams together, and also the angle at which they cross each other when they meet in the center of the detectors. But we don't get to decide exactly which ones collide. Okay, so okay, I can also see that there were a bunch of questions during the live about dancing during the inauguration. I think that's probably about the Gotthard tunnel. That's nothing to do with CERN. The Gotthard tunnel is a train tunnel that was built in Switzerland. I think it's about 50 kilometers long. I forget exactly how long it is, but anyway, it was built as a tunnel for trains. And when they finished the tunnel, they had a ceremony, and because it goes through a mountain, they had some it was weird. You know, it's artistic. It depends on what your favorite type of art is. But it wasn't based at CERN. But I think because it's a tunnel and it's Switzerland, people think that it was a CERN event, but it wasn't anything to do with us. So Carlos says that they're 21 and have been thinking about going back to school for a major in astrophysics. Is that okay? Absolutely. I mean, if that's what you want to do, it's that's still very young to be going, and many people go and do degrees slightly later. And honestly, I kind of wish maybe I'd taken a little bit of more time. I sort of rushed through my education for various different reasons, including the fact that the cost of university in the UK went up when I was applying, and I didn't want to get landed then with a much, much higher bill for my university education. So I went as quickly as possible, but I think having taken some time, gotten some different world experience, and then coming back is going to also ground you maybe a little bit more and give you more opportunities to use those skills that you've picked up during your education. So I think it's fantastic if you're deciding to go back, and you shouldn't let the fact that it's been a little bit later put you off going. In fact, when I did my PhD, there was a guy who had retired from a very long career and decided that the thing he wanted to do before he properly retired was go and get a PhD in physics. So he came back to do his PhD before he then properly settled into his retirement. So it's absolutely never too late to keep learning. And also the point in making these videos and sharing the videos that I do online is that I think it's also never too late to just learn about how our universe works. And so that's what I hope to be able to share with you in these videos, and to answer the questions that people have about particle physics and physics in general. So I think being curious and learning more about how our universe works at any time is a great idea. So there's a question here, which I think is a great, there's three questions here I'm gonna finish with. They all come from TikTok. And then if I didn't get your question, please, as I said before, do put them in the chat of the video and I'll try and come back later. So the three that I'm gonna try and answer are, would you believe dark matter will be discovered, or may we try finding some other concept? We know that dark matter is in our universe. There is something that is causing this gravitational effect. It's 5 times more massive than the regular matter that we have in our universe in total. We don't know what it is individually. I'm sure eventually we'll work out what it is. As a species, we are very intelligent and very curious, and we've learned so much about our universe already that I do believe that we're going to work out what it is. But the specifics of what it is just depends on what nature has for us. And that then depends how long it'll take, because perhaps we need higher energies, perhaps we need to look further out into the universe, perhaps we need to collect more data. We'll just have to see. But one of the things that also keeps me going is the fact that when we do these grand scale science experiments, when we create an experimental facility like the Large Hadron Collider, or when we send telescopes out into space, we come together as a community, as scientists, and as just curious people in general, and we push the boundaries of what we're capable of, and we get so much incredible technology and understanding just from that process, that for me, that's why I'm quite happy to dedicate my time during my life to doing this kind of research, because even if I don't get to find out what dark matter is now, I believe this is a worthwhile human endeavor to do. And it brings us together as people from different places and allows us to work on something peaceful and something curious. So I definitely think it's worth doing, but I really hope, I would love to know what dark matter is sorry, I didn't turn off my notifications today, before I stop being around. Then there's a question, is it hypothesized that normal matter would pass through dark matter? So yeah, that's kind of what we're seeing, because normal matter and dark matter aren't interacting. There's a really incredible picture called the bullet cluster image, so you can go look that up. And it is 2 galaxies, right, colliding together, and we can see the distribution of the mass from the regular matter, and we can also predict where the dark matter is in this image, and we can see that the regular matter is sort of interacting with each other in the center of this image, and the dark matter is much more spread out, so it's passed through and not collided, and then the regular matter is in the center of this image, which is another one of these pieces of evidence that we have for dark matter existing. And then I'm going to finish on a fun one. There's a question, do you believe in the multiverse? Believe is the correct word there, because we don't have any scientific evidence either way. I think it's really fun to think about, and there's a lot of great sort of thought experiments. I'm not going to embarrass myself by saying it in German, which is what Einstein used to call them, but thought experiments where you can push the ideas of how our universe works to the very different ways. And so the multiverse is one of those, but we don't have any evidence. So again, as an experimental physicist, if you separate the sort of physicist side of me, then I would say, I don't know, because there's no evidence, so I don't really think about it. But then as somebody who enjoys Marvel and a bunch of other sci-fi content, I love thinking about the different ways that the universe could exist in a much more grand way. Although, I mean, saying that, everything we're learning about the universe is very grand, but I'm talking more about science fiction than the experimental data that we have. So do I believe that was the question? I don't know. Even if even if not, even if the multiverse doesn't exist and this is all that we have, I think it's already incredibly enough. There's so much going on in our universe already. But there are different hypotheses. You should read Katie Mack's book, Dr. Katie, about the end of the universe, because she also talks about potentially other universes, multiverses, a little bit in that. So that's a really great book to read more about that as well. Okay, I am gonna wrap things up so that I can finish. I really didn't drink very much of my tea again, but I did quite enjoy using my Euclid mug. And yeah, any questions that I didn't manage to answer? Oh, the name of the book is called The End of Everything, the Katie Mack's book. So you should definitely go and check that out. She's a fantastic writer, so funny. You would think that would be a really morbid topic, the end of the universe, but she makes it so fun. So yes, thank you so much for joining. I am going to wrap this up. Thanks again, Bob, for moderating the chat. You did a fantastic job, and it's really great to have you here. So you should go and check out Bob's channel, Fundamentally Explained. He makes really, really nice animated videos about particle physics. So you should go and watch those. Somebody says, should I buy Bitcoin? Absolutely not. Save your money. I'm not an economist, so take that as you will. Yeah, thanks again for the questions. Thanks for hanging out with me. I had so much fun. Happy Dark Matter Day. Sorry it was a day late. I wasn't flying the plane, so I couldn't get it to leave any earlier. But yeah, it was really great to hang out and have all your questions. And I will see you in the next live. Before I do go, I've got some exciting videos that I am trying to edit. These are going to be longer videos for you to watch. So I've got one that's coming up that's about how we upgrade the Atlas detector. So I talked a little bit about when I was a PhD student and a postdoc, when I was building the next or developing detectors for the next version of the Atlas experiment. And at NICEF, we are doing that construction for the next version of the Atlas tracker. So I interviewed one of my colleagues who's working in the clean room developing that, and she's explaining how we're doing that upgrade. So I'm really excited to share that video with you. You can learn more about how we prepare for the next stage of the Large Hadron Collider when we're going to go to what we call the high luminosity LHC, where we squeeze those beams even closer together, as I was talking about how they collide, and we get many, many more collisions happening each time those bunches cross, which is going to be a huge challenge, not only for the detector, but also for the data acquisition teams and the being able to calibrate and understand all that data. But more data means that then hopefully we can look for even rarer processes, isolate the signals better that we're looking for, and that will hopefully help us understand dark matter if we can find signals of it in our detector. And then I have another video coming up. So I went to visit the antimatter factory that we have at CERN, and I had another colleague who showed me around there and talked about her work on measuring the gravitational effect on antimatter. So we've been talking about dark matter today. That video is about antimatter. They're different things, but we've still got many questions about antimatter as well. So I'm really excited about these two videos. They are longer than my usual content, go more into depth of the physics. So hopefully they will be out as soon as I can sit down and edit them. But I can't wait to share those with you. And then there's a question, where can we get a sweater like yours? I don't know if these are still available. This is an ESA jumper, but they do have some awesome awesome ESA jumpers on the website. So you can order those and get them sent to you. So I don't know if they do this one. This was a specific Halloween one that they sent last year. But they've got lots of really fun gear on their website. Okay, so I am going to wrap things up now, finish my tea, probably send a few emails and then call it a night. Thank you again for joining, and I will see you very soon in another live. And yeah, thanks so much again, Bob, for moderating the chat. Have a great evening, everyone, or day, wherever you're joining from. Yeah. Oh, quickly before I go, the name of the author was Katie Mack. If you look for The End of Everything, then you'll be able to find the book. All right, folks. Thanks for joining. See you later.